Tonight, we're going to embark on a journey to one of the most extreme places in our entire solar system, a world where temperatures can swing from hot enough to melt, lead during the day, to cold enough to freeze nitrogen at night. A place where the sun looms enormous in the sky, yet shadows harbor ice that may have existed for billions of years. We're going to explore Mercury, the smallest planet, the fastest planet, and arguably the most mysterious of all the rocky worlds orbiting our sun. By the time this journey ends, you will understand a planet that has puzzled astronomers for millennia and continues to surprise scientists with every new observation we make. Before we begin, if you enjoy these deep explorations of the cosmos and find them relaxing, a quick like or subscribe would really help the channel grow. Now let us turn our gaze toward the innermost planet of our solar system and discover what makes Mercury such an extraordinary world. Long before telescopes existed, long before humans understood what planets truly were, ancient civilizations gazed at the night sky and noticed something peculiar. Among the countless fixed stars that wheeled overhead in their predictable patterns, there were a handful of wanderers, celestial objects that moved against the background of stars in complex paths that seemed almost willful. The Greeks called them planets, meaning wanderers, and among these wanderers was one that moved faster than all the others, darting across the heavens with remarkable speed, never straying far from the brilliant glow of the sun. The earliest known recorded observations of this swift wanderer come from ancient Mesopotamia. The Mul.apn tablets, compiled by Babylonian astronomers around 1000 BC, but likely based on observations dating back several centuries earlier, contain references to this planet using a cuneiform name that translates to something like the jumping planet, a fitting description for a world that seems to hop from one side of the sun to the other as viewed from Earth. The Babylonians, those remarkable astronomers who laid the foundations of systematic skywatching, called the planet Nabu, naming it after their messenger god, who presided over knowledge, writing, and communication. These ancient observers tracked Mercury's movements carefully, recording their observations on clay tablets that have survived to this day. The ancient Greeks initially believed they were observing two different celestial objects. When the bright point of light appeared in the morning sky before sunrise, they called it Apollo, associating it with the god of light and the sun. When that same point of light appeared in the evening sky after sunset, they called it Hermes, the messenger god known for his speed and cunning. It was not until around 350 BC that Greek astronomers realized these morning and evening stars were actually the same celestial body. They settled on the name Hermes, recognizing that the planet's swift movement across the sky made it a fitting representative of the fleet-footed messenger of the gods. The Romans, who adopted and adapted much of Greek astronomy and mythology, renamed the planet Mercury after their own messenger god who served as the intermediary between the divine realm and the mortal world. Mercury, like Hermes before him, was depicted with winged sandals and a winged helmet, symbols of his legendary speed. He carried a caduceus, a staff entwined by two serpents, and was considered the god of commerce, travel, and communication. The name stuck, and to this day, we call the innermost planet Mercury in most Western languages. But the Greeks and Romans were far from the only cultures to observe and name this elusive world. In ancient China, Mercury was known as Chengxing, the hour star, and was associated with the direction north and the element of water in the five phases system of metaphysics. Modern Chinese, as well as Korean, Japanese, and Vietnamese cultures continue to refer to the planet as the water star. Hindu mythology called the planet Buddha, not to be confused with the Buddha, and believed this celestial deity presided over Wednesday and influenced intelligence and communication. The Germanic peoples associated the planet with Odin, also known as Woden, their chief god, who was connected to wisdom, poetry, and death. This association is preserved in the name Wednesday, which derives from Woden's Day. The Maya civilization may have represented Mercury as an owl, or possibly 4 owls, with 2 representing the morning aspect and 2 representing the evening aspect, serving as messengers to the underworld. If you want to see Mercury for yourself, you face the same challenge that has confronted observers throughout history. Mercury never strays far from the Sun as seen from Earth. Its apparent distance from our star never exceeds about 28 degrees, which means you can only observe Mercury during brief windows of time, either shortly after sunset, when it appears as an evening star low on the western horizon, or shortly before sunrise, when it shines as a morning star low on the eastern horizon. This proximity to the Sun makes Mercury the most elusive of the 5 planets visible to the unaided eye. You need a clear horizon, minimal light pollution, and good timing. When conditions are right, Mercury appears as a bright point of light that may have a slight pinkish or yellowish tinge depending on atmospheric conditions. The difficulty in observing Mercury contributed to centuries of incomplete understanding. Even after the invention of the telescope, Mercury remained challenging to study. Galileo Galilei observed Mercury in the early 17th century with his revolutionary but crude telescope, but his instrument was not powerful enough to reveal the planet's phases. It was not until 1639 that astronomer Giovanni Zuppi discovered that Mercury displayed phases similar to Venus and the Moon, proving that the planet orbited the Sun rather than Earth. This observation supported the heliocentric model of the solar system that Copernicus had proposed and Galileo championed. The observation of Mercury's phases was an important piece of evidence for the Copernican system. In the Earth-centered Ptolemaic model, Mercury always remained between Earth and the Sun, so it could never display a full phase like Venus could when it passed on the far side of the Sun from Earth. But in a heliocentric model, both Mercury and Venus would show phases as they orbited the Sun, sometimes between us and the Sun showing crescent phases, and sometimes on the far side of the Sun showing gibbous or full phases. The confirmation of Mercury's phases helped establish that the Sun, not Earth, was the center of the planetary system. For centuries, astronomers struggled to map Mercury's surface and determine its rotation period. The planet's proximity to the Sun made observations difficult and brief. When Mercury is at greatest elongation, its maximum apparent distance from the Sun, it can be observed for a few hours in the morning or evening sky, but even then it is low on the horizon, where atmospheric turbulence distorts the view. Attempting to observe Mercury when it is higher in the sky means observing during daylight, when the bright sky background makes the planet difficult to see. Italian astronomer Giovanni Schiaparelli, famous for his observations of Mars, spent years studying Mercury in the late 19th century. He concluded that Mercury was tidally locked to the Sun, meaning that one side of the planet always faced the sun, while the other remained in perpetual darkness, similar to how the moon always shows the same face to Earth. This seemed logical given Mercury's closeness to the sun, and the idea persisted for decades. Schiaparelli's conclusion was based on the features he observed appearing at the same positions each time Mercury was favorably placed for observation. The French astronomer Eugène Antoniadi, observing in the early 20th century at the Meudon Observatory near Paris, also studied Mercury extensively and agreed with Schiaparelli's conclusion about synchronous rotation. Antoniadi produced detailed maps of Mercury's surface features, labeling light and dark regions with names that evoked classical mythology. Though these early maps have been superseded by spacecraft data, they represent a remarkable achievement of telescopic observation of an extraordinarily difficult target. It was not until 1965 that astronomers discovered the truth. Radar observations conducted by scientists bouncing radio waves off Mercury's surface revealed something unexpected. The planet was not tidally locked at all. Instead, Mercury rotated 3 times for every 2 orbits around the Sun, a peculiar arrangement called a 3.2 spin-orbit resonance. This discovery overturned decades of assumptions and opened new questions about this enigmatic world. The astronomers who had observed Mercury and thought they were seeing the same features repeatedly had not been wrong in their observations. They had simply caught Mercury at the same point in its resonance cycle, which happens to coincide with good observing opportunities from Earth. The radar observations that revealed Mercury's true rotation were conducted using the powerful 305-meter radio telescope at the Arecibo Observatory in Puerto Rico by astronomers Gordon Pettengill and Rolf Dice. By transmitting radio waves toward Mercury and analyzing the reflected signals, scientists could determine how fast the planet was rotating. The Doppler shift of the reflected waves from the approaching and receding edges of the planet's disk revealed the rotation rate. This technique, developed in the 1960s, opened a new era of planetary radar astronomy that has since been used to study many solar system objects. Mercury occupies a unique position in our solar system. It is the innermost planet, orbiting closer to the Sun than any other world in our cosmic neighborhood. At its closest approach to the Sun, a point called perihelion, Mercury comes within approximately 46 million kilometers, or about 29 million miles, of our star. At its farthest point, called aphelion, Mercury swings out to about 70 million kilometers, or roughly 43 million miles, from the Sun. This represents a significant variation in distance, and Mercury holds the distinction of having the most eccentric orbit of any planet in the solar system, with an eccentricity of 0.21. To understand what this means, imagine drawing an ellipse on a piece of paper. The eccentricity describes how elongated that ellipse is compared to a perfect circle. A circle has an eccentricity of 0, while a very elongated ellipse approaches an eccentricity of 1. Mercury's eccentricity of 0.21 means its orbit is noticeably stretched, resulting in a substantial difference between its closest and farthest distances from the Sun. This eccentric orbit has profound effects on the planet's environment and behavior. Mercury completes one orbit around the Sun in approximately 88 Earth days. This is Mercury's year, and it makes Mercury the fastest planet in the solar system in terms of orbital speed. At perihelion, when Mercury is closest to the Sun and the Sun's gravitational pull is strongest, Mercury races through space at nearly 59 kilometers per second, or about 132,000 miles per hour. At aphelion, its speed drops to about 39 kilometers per second, or roughly 87,000 miles per hour. Even at its slowest, Mercury moves through space faster than any other planet. The relationship between Mercury's rotation and its orbit is one of the strangest features of this already strange world. As mentioned earlier, Mercury rotates 3 times for every 2 orbits around the Sun, a 3.2 spin orbit resonance. One rotation of Mercury, what we might call a sidereal day, measured against the background stars, takes approximately 58.65 Earth days. But this is not the same as a solar day on Mercury, which is the time from one sunrise to the next, as experienced on the surface, because Mercury rotates slowly while simultaneously moving rapidly around the Sun in an eccentric orbit. The relationship between its rotation and its orbit creates some truly bizarre effects. A solar day on Mercury, from one sunrise to the next at a given location, lasts about 176 Earth days. This is roughly 2 Mercury years. Imagine that. On Mercury, a single day-night cycle takes longer than 2 complete trips around the Sun. The Sun rises, crawls across the sky, sets, and the long night begins. And by the time the Sun rises again, 2 years have passed. But it gets stranger still. The combination of Mercury's 3-2 resonance and its highly eccentric orbit produces a phenomenon that would seem deeply alien to anyone standing on Mercury's surface. At certain longitudes on Mercury, the Sun performs a peculiar dance in the sky. As the Sun approaches the zenith, it actually appears to stop, reverse its motion briefly, and then continue forward again. This is because Mercury's orbital speed varies significantly depending on its distance from the Sun. Near perihelion, when Mercury is moving fastest, its orbital angular velocity temporarily exceeds its rotational angular velocity. From certain locations on the surface, this makes the Sun appear to move backward in the sky before resuming its normal path. At other locations, an observer would see the Sun rise, set partially back below the horizon, and then rise again before continuing its journey across the sky. This double sunrise or sunset is unique to Mercury among the planets of our solar system. The varying distance between Mercury and the Sun during its orbit has dramatic effects on how the Sun appears from Mercury's surface. At perihelion, the Sun appears about 1.5 times larger than it does at aphelion. If you could stand on Mercury's equator at perihelion, the Sun would appear more than 3 times larger in diameter than it does from Earth's surface, and the sunlight would be roughly 11 times more intense. At aphelion, the Sun would appear somewhat smaller, but still about 2 times larger than we see it from Earth, with sunlight about 4.5 times more intense than on our home planet. Mercury's axial tilt, the angle between its rotational axis and the plane of its orbit, is remarkably small, only about 0.034 degrees. This is the smallest axial tilt of any planet in the solar system. For comparison, Earth has an axial tilt of about 23.4 degrees, which is what causes our seasons as different hemispheres receive more direct sunlight during different parts of the year. Mercury's nearly perpendicular orientation means the planet experiences essentially no seasons. But more importantly for our story, this tiny axial tilt means that Mercury's polar regions receive very little direct sunlight. The floors of craters at the poles may never see the Sun at all, creating pockets of permanent shadow that, as we will discover later, harbor surprising secrets. The synodic period of Mercury, which is the time between successive alignments of Mercury, Earth, and the Sun is approximately 116 days. This is the interval between one inferior conjunction when Mercury passes between Earth and the Sun and the next. During inferior conjunction, Mercury is at its closest to Earth, sometimes approaching within 77 million kilometers. However, at this time, Mercury presents its dark side to us and is lost in the Sun's glare. During superior conjunction, when Mercury is on the far side of the Sun from Earth, the planet can be as far as 222 million kilometers away. A fascinating consequence of orbital mechanics is that despite being farther from the Sun than Mercury's average distance, Earth is actually closest to Mercury more often than to any other planet. This counterintuitive result arises because Mercury's rapid orbit keeps it relatively near Earth much of the time, while the outer planets spend long periods on the far side of their orbits. On average, Mercury is the closest planet to Earth, and indeed to every other planet in the solar system, simply because it spends the most time in close proximity due to its small, fast orbit. Mercury occasionally passes directly across the face of the Sun as seen from Earth, an event called a transit. Transits of Mercury occur roughly 13 times per century, making them much more common than transits of Venus. For a transit to occur, Mercury must be at, or very near, inferior conjunction at the same time that Earth is positioned, such that Mercury's orbital plane intersects our line of sight to the Sun, because Mercury's orbit is inclined about 7 degrees to the ecliptic. The plane of Earth's orbit transits can only happen in early May or early November, when Earth crosses the line of nodes, the line where Mercury's orbital plane intersects the ecliptic. The first recorded observation of a Mercury transit was made by French astronomer Pierre Gassendi on November 7, 1631. Gassendi had been alerted to the possibility by Johannes Kepler, who predicted both Mercury and Venus transits based on his laws of planetary motion. The observation of Mercury's tiny dark disk crossing the Sun confirmed the heliocentric model and demonstrated that Mercury was much smaller than previously thought. Throughout the 17th, 18th, and 19th centuries, astronomers observed Mercury transits to refine their understanding of the planet's orbit and to attempt measurements that could determine the size of the solar system. More recent transits of Mercury occurred in May 2016 and November 2019. These events were widely observed and broadcast worldwide, with images from ground-based and space-based telescopes showing Mercury as a tiny black dot against the brilliant solar disk. The next transit of Mercury will not occur until November 2032. During a transit, Mercury appears as a perfectly round, jet-black circle, about 1/160th the apparent diameter of the Sun. Even a small telescope can reveal the transit, though proper solar filters are absolutely essential to protect the eyes from the Sun's intense light. Mercury is small. It is the smallest planet in our solar system, and by a considerable margin when compared to the next smallest planet, Mars. Mercury's diameter is approximately 4,180 kilometers, or about 332 miles. To put this in perspective, Mercury is only about 38% the diameter of Earth. If Earth were the size of a baseball, Mercury would be about the size of a golf ball. Mercury is so small that 2 moons in our solar system, Jupiter's Ganymede and Saturn's Titan, are actually larger in diameter than Mercury, though neither is as massive. The surface area of Mercury is about 74.8 million square kilometers, roughly the same as the total land area of Africa and Asia combined. Despite being the smallest planet, Mercury's surface area is still vast by human standards, representing an enormous expanse of cratered terrain, volcanic plains, and mysterious geological features waiting to be explored in detail. Mercury's small size has important consequences for its geology and evolution. Small bodies lose their internal heat more quickly than large ones because they have a larger surface area to volume ratio. Heat generated by radioactive decay in the interior and residual heat from formation can escape more efficiently to space. This is why Mercury's interior has cooled and solidified more extensively than Earth's interior, and why Mercury lacks the plate tectonic activity that continues to reshape Earth's surface. Despite its diminutive size, Mercury is surprisingly hefty for its dimensions. Mercury has a mass of approximately 3.30 times 10 to the 23rd power kilograms. While this is only about 5.5% of Earth's mass, Mercury packs this mass into a much smaller volume, giving it an impressively high density. In fact, Mercury is the second densest planet in the solar system, with a density of about 5.427 grams per cubic centimeter. Only Earth is denser, at about 5.515 grams per cubic centimeter. But here's the crucial detail. If you were to factor out the effects of gravitational compression, which squeezes planetary interiors under immense pressure, Mercury would actually be the densest planet. Earth's high density is partially due to the crushing pressure at its core. Mercury, being much smaller, experiences less gravitational compression, yet it still achieves nearly the same density. The materials that make up Mercury must therefore be inherently denser than those composing any other planet. To appreciate what this means, consider that Mercury's uncompressed density, the density its materials would have, if not squeezed by gravity, is about 5.3 grams per cubic centimeter, while Earth's uncompressed density is only about 4.0 to 4.4 grams per cubic centimeter. This remarkable difference tells us that Mercury is made of fundamentally different stuff than Earth, stuff that is denser even before any compression is applied. This extraordinary density tells us something fundamental about Mercury's composition. Mercury is made primarily of metal, specifically iron. While all the rocky inner planets have iron cores, Mercury's core is proportionally enormous. Scientists estimate that Mercury's iron-rich core has a radius of about 2,074 kilometers, or roughly 189 miles. This means the core extends to approximately 85% of the planet's radius. In terms of volume, Mercury's core occupies about 55% of the planet's total volume, compared to about 17% for Earth. In terms of mass, the core accounts for approximately 60 to 70% of Mercury's total mass. Mercury is essentially a giant ball of iron wrapped in a relatively thin rocky shell. The mantle and crust of Mercury are correspondingly thin. The mantle, composed primarily of silicate minerals, is only about 400 to 600 kilometers thick. The crust, the outermost solid layer, ranges from perhaps 25 to 125 kilometers in thickness depending on location. This thin outer shell represents all the rocky material that separates Mercury's molten and solid iron interior from the harsh environment of space. If Mercury were an apple, the mantle and crust together would be thinner than the apple's skin. Standing on Mercury's surface, you would experience a gravitational pull significantly weaker than on Earth. Mercury's surface gravity is about 3.7 meters per second squared, roughly 38% of Earth's gravity. If you weigh 100 kilograms on Earth, You would weigh only about 38 kilograms on Mercury. You could jump roughly 2.5 times higher on Mercury than you could on Earth, and objects would fall more slowly. However, Mercury's gravity is still strong enough that the planet has held onto some atmosphere, however tenuous, and strong enough that escaping Mercury's gravitational pull requires a velocity of about 4.3 kilometers per second. Mercury's escape velocity of 4.3 kilometers per second is less than half of Earth's escape velocity of 11.2 kilometers per second. This relatively low escape velocity, combined with the intense heating from the nearby sun, makes it very difficult for Mercury to retain atmospheric gases. Any substantial atmosphere would gradually boil away into space, a process called Jean's escape, as the fastest-moving gas molecules exceed the escape velocity and depart forever. This is why Mercury has only an exosphere rather than a true atmosphere. The temperature extremes on Mercury are legendary. Without a substantial atmosphere to trap heat or moderate temperatures, Mercury experiences the most extreme temperature variations of any planet in the solar system. During the long Mercurian day, surface temperatures on the sunlit side can soar to approximately 430 degrees Celsius, or about 800 degrees Fahrenheit. This is hot enough to melt lead, zinc, and tin. If you could somehow stand on Mercury's dayside equator at solar noon, you would witness a landscape broiling under relentless radiation from an enormous sun that fills a significant portion of the sky. The hottest locations on Mercury are the so-called hot poles, 2 points on the equator at longitudes 00 and 180 degrees, where the sun is directly overhead at perihelion. At these locations, the combination of Mercury's closest approach to the sun and the sun's position at the zenith creates the most extreme heating conditions on the planet. Temperatures at the hot poles can reach even higher than the average daytime temperatures, approaching 450 degrees Celsius under optimal conditions. Yet when night falls on Mercury, the same surface that was hot enough to melt metal rapidly cools to astonishing lows. Without an atmosphere to retain heat, the energy radiates away into space. Nighttime temperatures on Mercury can plunge to approximately negative 180 degrees Celsius, or about negative 290 degrees Fahrenheit. This is colder than the nighttime surface of the moon and colder than many objects in the outer solar system. The temperature difference between Mercury's daytime highs and nighttime lows can exceed 600 degrees Celsius, a swing unmatched by any other planet. This extreme diurnal temperature variation has interesting implications for the subsurface. While surface temperatures swing wildly between day and night, conditions just a few meters below the surface are much more stable. The rocky regolith, the layer of broken and powdered rock covering Mercury's surface, acts as an insulator. Solar heat penetrates slowly into the ground during the day, and the stored heat radiates slowly back to space during the night. At depths of a few meters, temperatures remain nearly constant regardless of whether it is day or night above. This subsurface thermal stability is one reason why ice can persist at the poles, despite the harsh radiation environment at the surface. Here is a counterintuitive fact that often surprises people. Despite being the closest planet to the Sun, Mercury is not the hottest planet in the solar system. That distinction belongs to Venus, whose thick carbon dioxide atmosphere creates a runaway greenhouse effect that maintains surface temperatures around 465 degrees Celsius, or about 869 degrees Fahrenheit, day and night, across the entire planet. Venus is consistently hotter than Mercury's daytime temperatures and enormously hotter than Mercury's nighttime temperatures. Mercury's lack of atmosphere means it cannot trap heat the way Venus does, so while Mercury gets more solar radiation, it cannot retain it. The stark contrast between Mercury and Venus illustrates the profound importance of atmospheres in determining planetary temperatures. Mercury receives roughly 10 times more solar energy per unit area than Venus at its orbit. Yet Venus is hotter because its atmosphere prevents the escape of thermal radiation. If Mercury had an atmosphere like Venus, it would be the hottest object in the inner solar system. Conversely, if Venus lost its atmosphere, it would cool dramatically despite being farther from the Sun than Mercury. Understanding these relationships helps scientists appreciate how atmospheres interact with stellar radiation to determine conditions on planetary surfaces. The interior of Mercury has been a source of fascination and puzzlement for planetary scientists since the first close-up observations were made in the 1970s. Mercury's enormous iron core raises profound questions about how the planet formed and what happened to all the rocky material that should, by most models, make up a much larger fraction of the planet's mass. Understanding Mercury's interior is crucial to understanding its history and the processes that shaped the inner solar system. Modern understanding of Mercury's internal structure comes primarily from data collected by NASA's Messenger spacecraft, which orbited the planet from 2011 to 2015. By carefully measuring how Mercury's gravity affected Messenger's orbit, and by analyzing the planet's rotation and magnetic field, scientists have constructed detailed models of Mercury's interior. What they found was remarkable. Mercury's core is not a simple, solid ball of iron. Instead, it appears to have a complex layered structure similar in some ways to Earth's core. At the very center of Mercury lies a solid inner core composed primarily of iron and possibly some nickel. This inner core is surrounded by a liquid outer core layer, also iron-rich, but containing lighter elements that keep it molten. Outside the liquid outer core is a solid metallic layer. The entire core assembly is wrapped in a thin mantle and crust composed of silicate rocks. The presence of a liquid outer core is particularly significant because it helps explain one of Mercury's most surprising features, its magnetic field. Mercury has a global magnetic field, which came as a surprise to scientists when Mariner 10 detected it in 1974. Magnetic fields in planets are typically generated by the motion of electrically conducting fluids in their interiors, a process called the dynamo effect. Earth's magnetic field is generated by convection in its liquid iron outer core. Before Mariner 10, many scientists assumed Mercury's core had completely solidified long ago given the planet's small size and the billions of years since its formation. A solid core cannot generate a dynamo-driven magnetic field. The discovery that Mercury does have a magnetic field implied that at least part of its core must still be liquid. Messenger confirmed and expanded upon these findings. The spacecraft's magnetometer measured Mercury's magnetic field in detail, revealing that it is about 1.1% as strong as Earth's magnetic field. At Mercury's equator, the field strength is roughly 300 nanotesla, compared to about 30,000 to 60,000 nanotesla for Earth's equatorial field. Mercury's magnetic field is weak, but it exists, and it is approximately a dipole. Similar in overall shape to Earth's field, but with one very peculiar feature. Mercury's magnetic field is offset from the center of the planet. The magnetic dipole, the imaginary bar magnet that best represents Mercury's field, is displaced northward by about 20% of the planet's radius, roughly 480 to 500 kilometers north of the planet's center. This offset was completely unexpected and has no parallel among other planets with dynamo-generated magnetic fields. The reason for this offset remains an active area of research, though models suggest it may be related to asymmetries in the convection patterns within Mercury's liquid outer core. The magnetic field, weak as it is, creates a magnetosphere around Mercury, a bubble of space dominated by the planet's magnetic field rather than the Sun's. Mercury's magnetosphere is tiny compared to Earth's, small enough to fit within Earth's magnetosphere if the two were somehow nested. Yet it is strong enough to deflect some of the solar wind, the constant stream of charged particles flowing outward from the Sun. During MESSENGER's flybys and orbital mission, scientists observed that Mercury's magnetosphere is highly dynamic, responding rapidly to changes in the solar wind. They discovered what they called magnetic tornadoes, twisted bundles of magnetic field lines connecting Mercury's magnetic field to the interplanetary magnetic field. These structures can be up to 800 kilometers wide and allow solar wind particles to penetrate deep into Mercury's magnetic environment, bombarding the surface and contributing to the generation of Mercury's thin exosphere. Why does Mercury have such an enormous core relative to its size? This question strikes at the heart of planetary formation theory and has generated several competing hypotheses over the decades. The most widely discussed explanation is the giant impact hypothesis. According to this scenario, Mercury originally formed with a composition similar to other rocky material in the early solar system, with a metal-to-silicate ratio resembling that of chondrite meteorites. At that time, Mercury may have been about 2.25 times its current mass. Early in the solar system's history, perhaps during the late heavy bombardment or earlier, a massive object, possibly a planetesimal several thousand kilometers across, with about 1/6 of Mercury's original mass, collided with the young planet. This catastrophic impact stripped away much of Mercury's rocky mantle and crust, leaving behind the iron core as a dominant component. A similar process, known as the giant impact hypothesis for the Moon's formation, is believed to have created Earth's moon when a Mars-sized body collided with the early Earth. For many years, this giant impact scenario was considered the leading explanation for Mercury's composition. However, data from the MESSENGER mission complicated this picture. MESSENGER discovered that Mercury's surface contains surprisingly high levels of volatile elements, including sulfur, potassium, and sodium. These elements are relatively easily vaporized and driven off by high temperatures. A catastrophic giant impact should have generated immense heat, potentially vaporizing Mercury's surface and driving off these volatile elements. Their presence on Mercury's surface today suggests either that the impact hypothesis is incomplete or that some mechanism restored these volatiles after the collision. Recent research has proposed alternative versions of the impact scenario that might resolve this contradiction. One idea suggests that Mercury was not the target of a collision, but rather the impactor. In this hit-and-run scenario, Proto-Mercury collided with a larger body, perhaps Proto-Venus or Proto-Earth, at a grazing angle. The collision stripped away much of Proto-Mercury's mantle, but because Mercury was the smaller body and escaped from the larger target, the stripped material did not fall back onto Mercury. Instead, it either remained with the larger body or was scattered through the inner solar system. This scenario could explain Mercury's high metal-to-silicate ratio while potentially preserving some volatile materials. Another recent study from 2025 proposed that a grazing collision between two similarly sized bodies could strip away about 60% of Proto-Mercury's original mantle. The researchers found that such grazing impacts are statistically much more common than the massive head-on collisions proposed in earlier theories, occurring in roughly 20% of simulated planetary systems. In this scenario, the gravitational influence of other forming planets and drag from the remaining gas and dust in the early solar disk would have prevented the stripped material from falling back onto Mercury. Alternative hypotheses exist that do not require a giant impact at all. One idea proposes that Mercury formed from the solar nebula before the young sun's energy output had fully stabilized. In this scenario, temperatures near Mercury's orbit could have been extremely high, potentially between 2500 and 3500 Kelvin, perhaps even approaching 10,000 Kelvin during certain phases. At such temperatures, much of Mercury's surface rock could have been vaporized, creating an atmosphere of rock vapor that was subsequently stripped away by the intense solar wind. Another hypothesis suggests that the solar nebula itself caused lighter particles to be separated from heavier particles in the region where Mercury was forming. Drag forces from the nebular gas might have preferentially removed silicate particles while allowing denser iron particles to accumulate, resulting in a planet with an unusually high metal content from the very beginning. Each hypothesis predicts different compositions for Mercury's surface, and scientists continue to analyze data from past missions and await new observations from Bepi Colombo to distinguish between these scenarios. The presence of volatiles on Mercury's surface seems to favor hypotheses that did not involve extreme heating, but the story is far from complete. The formation of Mercury remains one of the outstanding puzzles in planetary science. Mercury's surface tells the story of over 4 billion years of bombardment, volcanism, and tectonic activity. At first glance, Mercury resembles Earth's moon. Both worlds are covered in impact craters of all sizes, from tiny pits to massive basins hundreds of kilometers across. Both have large expanses of relatively smooth terrain that formed from ancient volcanic activity. Both lack substantial atmospheres and appear gray and barren. Yet closer examination reveals that Mercury is a distinct world with its own unique geological history. One of the first things to notice about Mercury's surface is its color, or rather, its relative lack of color. Mercury is a dark gray world, reflecting only about 10 to 12% of the sunlight that falls on it, making it slightly darker than the moon. The darkness is partly due to the presence of graphite, a form of carbon in the surface rocks. Messenger discovered that Mercury's darker regions have higher carbon content, suggesting that ancient graphite-rich rocks from Mercury's primordial crust are exposed in some areas. This dark material may be the remnant of a graphite flotation crust that formed when Mercury had a global magma ocean early in its history. the surface of Mercury is dominated by impact craters. These craters range from fresh, young features with bright ray systems extending across the landscape to ancient, degraded depressions that have been battered and modified by subsequent impacts over billions of years. The craters have been given names according to the International Astronomical Union's naming conventions for Mercury, which honor deceased artists, authors, composers, and musicians. You will find craters named for Beethoven, Tolstoy, Shakespeare, Debussy, Dickens, Homer, and many others. The practice gives Mercury's geography a cultural richness that reflects humanity's creative heritage. Some specific examples illustrate the range of figures honored on Mercury. The crater Debussy, 80 kilometers in diameter, is named for French composer Claude Debussy. Disney Crater honors Walt Disney. Tolkien Crater near Mercury's North Pole commemorates J.R.R. Tolkien. Lennon Crater recognizes John Lennon of the Beatles. Muddy Waters Crater honors the legendary blues musician. Dr. Seuss has a crater, as does Alvin Ailey, the pioneering dance choreographer. This naming convention transforms Mercury's cratered surface into a celebration of human artistic achievement. Mercury's craters exhibit the same general features found in impact craters throughout the solar system. Small craters are typically simple, bowl-shaped depressions. Larger craters develop more complex features, including central peaks, terraced walls, and surrounding ejecta blankets. The largest impacts created multi-ring basins, enormous structures with multiple concentric rings of mountains of valleys that record the tremendous energies released when massive objects struck the planet early in its history. Fresh craters on Mercury are surrounded by bright ray systems, sprays of lighter colored material that was excavated from below the surface and deposited across the surrounding terrain during the impact. These rays can extend for hundreds or even thousands of kilometers from the parent crater. Over time, space weathering darkens the ray material through exposure to solar wind particles and micrometeorite bombardment, so the presence of bright rays indicates a relatively young crater. Some of Mercury's most prominent ray systems emanate from craters like Mina, Hokusai, and Kuiper. The density of craters varies across Mercury's surface, and this variation tells us about the relative ages of different terrain. Heavily cratered regions are old, having accumulated impacts over billions of years. Smoother regions with fewer craters are younger, their surfaces having been reset by volcanic activity or other geological processes that erased earlier impact scars. By counting craters and comparing crater densities to models of the impact flux over solar system history, scientists can estimate the ages of different geological units on Mercury. The impact cratering record on Mercury provides a window into the history of bombardment in the inner solar system. Mercury, like the Moon and Mars, preserves ancient surfaces that record the late heavy bombardment, an intense period of impacts that occurred roughly 3.8 to 4.1 billion years ago. Understanding the timing and intensity of this bombardment is crucial for understanding the early evolution of all the terrestrial planets, including Earth, where the geological record from this period has been largely erased by subsequent geological activity. Two main types of plains terrain cover significant portions of Mercury's surface. The older terrain is called intercrater plains, gently rolling or hilly surfaces found between larger craters. These intercrater plains appear to have obliterated many earlier craters and show a scarcity of smaller craters, below about 30 kilometers in diameter. Scientists are still debating whether these plains are volcanic in origin or whether they represent material emplaced by the ejecta from large impacts. The intercrater plains are distributed fairly uniformly across Mercury's surface and represent some of the oldest visible terrain on the planet. The second type of plains terrain is called smooth plains. These are widespread flat areas that fill depressions of various sizes and bear a strong resemblance to the lunar maria, the dark basaltic plains that fill large basins on the Moon. The smooth plains on Mercury, however, have a different character than the lunar maria. Unlike the dark maria, Mercury's smooth plains have roughly the same albedo or reflectivity as the older intercrater plains. This makes them harder to distinguish visually, though their smoother texture and lower crater density reveal their younger age. Despite the lack of obvious volcanic features like volcanic vents or lava flows in early images, the distribution and shape of these plains strongly suggest they formed from volcanic activity. Lava-flooded low-lying areas burying older craters and creating the relatively smooth surfaces we see today. Messenger confirmed this interpretation by identifying volcanic vents along the margins of major basins. One of the most distinctive features of Mercury's surface is its system of lobate scarps. These are long, curved cliffs that can extend for hundreds of kilometers across the landscape and rise up to several kilometers in height. The scarps cut across craters and plains of various ages, indicating that they formed relatively late in Mercury's geological history, after most of the major impact bombardment had subsided. The scarps are thrust faults, geological structures formed when one block of crust is pushed up and over an adjacent block due to compressive forces. The presence of these lobate scarps tells us something fundamental about Mercury's history. The planet has been shrinking. As Mercury's interior cooled over billions of years, the liquid portions of its core gradually solidified. When iron solidifies, it contracts, taking up less volume than liquid iron. This contraction of the core caused the entire planet to shrink slightly. The shrinkage compressed Mercury's crust, causing it to buckle and thrust upward in places, creating the lobate scarps. Scientists estimate that Mercury has shrunk in diameter by as much as 7 kilometers since the end of heavy bombardment. This global contraction is unique among the terrestrial planets in its extent and expression. Earth has plate tectonics, which accommodates internal heat loss and allows the crust to be recycled. Venus appears to have had episodic resurfacing events. Mars has its own tectonic features, but nothing quite like Mercury's planet-wide pattern of compressional faulting. Mercury's lobate scarps are a direct record of planetary contraction written on the surface for scientists to read. Recent analysis of high-resolution messenger images revealed that Mercury's tectonic activity may not be entirely finished. Scientists discovered small-scale thrust fault scarps, only tens of meters high and a few kilometers long, that appear to be less than 50 million years old, and possibly much younger. These tiny scarps suggest that Mercury continues to contract and experience seismic activity even today. If you could place seismometers on Mercury's surface, you might detect Mercurian quakes caused by ongoing compression of the planet's interior. Mercury also preserves evidence of past volcanic activity beyond the smooth plains. Scientists have identified at least 51 pyroclastic deposits, areas where explosive volcanic eruptions scattered material across the landscape. About 90% of these pyroclastic deposits are found within impact craters, suggesting that impacts may have triggered or facilitated volcanic activity. The degradation state of the craters hosting these deposits indicates that pyroclastic volcanism occurred over a prolonged period in Mercury's history, not just during a single episode. Inside the southwest rim of the Caloris Basin, the largest impact structure on Mercury, scientists found a rimless depression consisting of at least 9 overlapping volcanic vents, each up to 8 kilometers in diameter. This complex represents a major volcanic center that was active well after the Caloris impact itself. The volcanic history of Mercury extends over billions of years, though the planet appears to have been geologically quiet for a very long time now. Mercury's crust contains some unusual compositional features. Messenger discovered that Mercury's surface is surprisingly low in iron for a planet with such an iron-rich interior. The iron content of the surface rocks is much lower than on the Moon or Mars. Instead, Mercury's crust is rich in sulfur, containing about 20 times more sulfur than Earth's crust. Calcium and magnesium-bearing sulfides are common on Mercury's surface. The presence of these compounds, along with other volatiles that Messenger detected, constrains theories of Mercury's formation and evolution. Another intriguing discovery is the presence of graphite in Mercury's crust. The less reflective regions on Mercury's surface appear to be rich in carbon, most likely in the form of graphite. Scientists have proposed that early in Mercury's history, when the planet had a global magma ocean, graphite floated to the surface because it is less dense than the silicate magmas. As the magma ocean solidified, this graphite-rich layer became incorporated into the planet's primordial crust. The dark material on Mercury may be the remnants of this ancient graphite layer, excavated and exposed by later impacts. Mercury may have the most carbon-rich surface of any rocky planet in our solar system. The Caloris Basin is Mercury's crown jewel, the largest and most spectacular impact feature on the planet, measuring approximately 1,550 kilometers, or about 960 miles. In diameter, Caloris is one of the largest impact basins in the entire solar system. To put its size in perspective, the basin is about 1/3 the diameter of the entire planet. The state of Texas could fit inside Caloris with room to spare. The name Caloris comes from the Latin word for heat, calor, a fitting designation considering the basin's location. Caloris is positioned at one of the 2 hottest points on Mercury's equator. Because of the peculiarities of Mercury's orbit and rotation, there are 2 longitudes on Mercury where the Sun is directly overhead, when the planet is at perihelion, its closest approach to the Sun. These so-called hot poles experience the most intense solar heating of anywhere on Mercury's surface. Caloris happens to lie at one of these locations, making it one of the most brutally hot places on the planet during the Mercurian day. The Caloris Basin was created by a catastrophic impact early in Mercury's history, estimated to have occurred between 3.8 and 3.9 billion years ago. This timing places the formation of Caloris near the end of the late heavy bombardment, a period when the inner solar system was being pummeled by a rain of asteroids and comets. The impactor that created Caloris must have been enormous, perhaps 100 to 150 kilometers across, striking Mercury with enough energy to reshape the planet's geology on a global scale. The energy released by the calorous impact was almost incomprehensibly large. Scientists estimate that the collision delivered energy equivalent to trillions of nuclear bombs detonating simultaneously. This energy excavated a hole nearly 1/3 the diameter of the entire planet through ejecta across Mercury's surface for thousands of kilometers and sent seismic waves reverberating through and around the planet. The impact would have created a blinding flash visible throughout the inner solar system, followed by a rain of molten rock falling back onto Mercury's surface. The basin is surrounded by the Calorus Montes, a ring of mountains approximately 2 kilometers high that formed from the ejecta thrown out during the impact. These mountains mark the outer rim of the basin and represent some of the highest terrain on Mercury. Outside this mountain ring, the impact ejecta extends for over 1,000 kilometers, creating a complex zone of radial ridges, valleys, and debris-filled plains. Concentric rings surround the basin at various distances, recording the tremendous shock waves that rippled through Mercury's crust during and after the impact. The impact that created Calorus was so powerful that it may have fundamentally altered Mercury's geological evolution. Some scientists have suggested that the impact could have triggered extensive volcanic activity by disrupting the thermal structure of Mercury's interior. Others have proposed that the impact affected Mercury's rotation or orbital parameters. While these more dramatic effects remain speculative, there is no doubt that Calorus represents one of the most significant geological events in Mercury's history. Similar giant impacts created other large basins on Mercury, though none as large as Calorus. The Rachmaninoff Basin, about 306 kilometers in diameter, is one of the most geologically interesting of the other basins, showing evidence of recent volcanic activity on its floor. The Rembrandt Basin, discovered by Messenger, spans about 715 kilometers and is the second largest basin on Mercury. Numerous smaller multi-ring basins dot the surface, recording the violence of the late heavy bombardment that scarred all the inner planets and moons. The floor of Calorus Basin tells a complex geological story. After the impact excavated the initial crater, volcanic activity filled much of the basin interior with lava, creating smooth plains that buried the original impact surface. These lavas appear orange in color-enhanced images from Messenger and have a different composition than the surrounding terrain. The floor is broken by a prominent pattern of ridges and fractures, arranged in roughly concentric and radial configurations. Wrinkle ridges formed by compression as the basin floor subsided under the weight of the volcanic infill are abundant. More than 200 fractures radiate from the center of the basin, many of them grabens, which are depressions bounded by faults. At the very heart of the Calorus Basin lies one of Mercury's most famous geological features, Pantheon Fossae, nicknamed the Spider by the Messenger science team. This structure consists of over 100 narrow, flat-floored troughs, radiating outward from a central point, creating a pattern that resembles the legs of an enormous spider spreading across the basin floor. Near the center of this radial pattern sits Apollodorus, a 40-kilometer diameter impact crater. When Messenger first returned detailed images of this region, scientists initially wondered whether Apollodorus crater was responsible for the radiating troughs. However, further analysis revealed that the crater probably formed after the troughs, landing coincidentally at the center of the spider. The exact cause of Pantheon fossae remains debated, with various hypotheses involving uplift of the basin floor, subsidence around the crater, or other tectonic processes. Perhaps the most bizarre consequence of the Caloris impact lies on the exact opposite side of Mercury, directly antipodal to Caloris, 180 degrees around the planet, is a unique geological region known as chaotic terrain or weird terrain. This area covers several 100,000 square kilometers and consists of hills and mountains up to 2 kilometers high, interspersed with valleys and smooth plains. The terrain is jumbled and disrupted, with none of the organized patterns seen elsewhere on Mercury. The leading hypothesis for the formation of this weird terrain involves the Caloris impact itself. According to this model, when the enormous impactor struck Mercury, it generated powerful seismic waves that traveled through and around the planet. Based on the geometry of Mercury's interior, these waves would have converged at the antipodal point, focusing their energy on the region directly opposite the impact site. This concentrated seismic energy, the hypothesis suggests, was sufficient to fracture and disrupt the crust, creating the chaotic landscape we see today. In essence, the Caloris impact appears to have been so powerful that it rang Mercury like a bell, and the vibrations shattered the surface on the other side of the world. Recent research has added nuance to this story. Studies of the chaotic terrain using messenger data suggest that the region's development continued long after the Caloris impact itself. Some of the surface appears to have collapsed due to the loss of volatile materials from subsurface layers, a process that may have extended until about 1.8 billion years ago, roughly 2 billion years after Caloris formed. The chaotic terrain may therefore record not just the violence of the Caloris impact, but also Mercury's long history of volatile loss and crustal evolution. Among the most unexpected features discovered by Messenger are Mercury's hollows. These are irregularly shaped, shallow depressions found scattered across the planet, typically in clusters within impact craters or on crater central peaks and walls. Hollows are generally bright compared to the surrounding terrain and have a characteristic blue color in enhanced images. They appear remarkably fresh, with sharp edges and floors that look relatively unweathered by meteorite bombardment. Many scientists believe hollows are among the youngest geological features on Mercury, possibly still forming today. Hollows were first spotted as bright, ill-defined patches by Mariner 10 in the mid-1970s, though their true nature was not understood at the time. The patches appeared again during Messenger's flybys, but it was not until Messenger entered orbit in 2011 and began capturing higher resolution images that these bright areas were revealed as shallow, irregularly shaped depressions on the surface. The orbital mission revealed their true prevalence across Mercury's surface. Thousands of hollow clusters have been identified, with individual hollows ranging from tens of meters to several kilometers across and up to tens of meters deep. They are particularly common within and around impact craters of all sizes, suggesting a connection between impact processes and hollow formation. Hollows appear to form when volatile material in Mercury's crust sublimates, transitioning directly from solid to gas and escaping into space. As the volatile material escapes, the surface collapses, creating the characteristic depressions. The volatiles involved may include sulfur, chlorine, or other compounds that can survive in Mercury's crust, but vaporize when exposed at the surface. Hollows are often associated with low reflectance material, the dark, graphite-rich terrain that may represent Mercury's primordial crust. The discovery of hollows demonstrated that Mercury is a more dynamic and geologically active world than anyone had imagined before Messenger arrived. The distribution of hollows provides clues about their formation. They are more common on sun-facing slopes and in equatorial regions, where solar heating is most intense, consistent with a sublimation-driven formation mechanism. However, they are also found in shadowed regions, suggesting that impact heating can also trigger hollow formation. When an impact excavates or heats volatile, rich material, it may initiate sublimation that continues long after the impact itself. The presence of hollows has important implications for understanding Mercury's composition and history. The existence of volatiles in Mercury's crust was surprising given the planet's proximity to the Sun and the high temperatures during its formation. If Mercury formed from very hot material, as some theories suggest, volatile compounds should have been driven off long ago. The persistence of volatiles near Mercury's surface, as evidenced by the hollows, constrains formation models and suggests that not all of Mercury's surface has been thoroughly devolatilized. Some scientists have suggested that hollows may provide indirect evidence for recent volcanic outgassing or other internal processes that could deliver volatiles to the near-surface environment. Others propose that the volatiles were present from Mercury's formation and have simply survived in locations that remained cold enough to prevent their escape. Regardless of their origin, hollows represent an active geological process that is reshaping Mercury's surface even in the present day, making the planet far more geologically interesting than a simple dead rock world. The youthful appearance of hollows raises intriguing questions about the timescales involved in their formation. If hollows form quickly once volatile material is exposed, their fresh appearance would not tell us much about their age. But if they form slowly over millions or billions of years, the presence of many fresh-looking hollows would suggest that the formation process is ongoing today. Understanding the rate at which hollows form is an active area of research that future missions like Bepa Colombo may help resolve. One of the most astonishing discoveries about Mercury is that this sun-scorched world harbors vast deposits of water ice. The idea that ice could exist on the closest planet to the Sun seems almost paradoxical, but the unique geometry of Mercury's orbit and rotation creates conditions that make this possible. Mercury's axial tilt is essentially zero, only 0.034 degrees. This means the Sun always appears at or very near the horizon, as seen from Mercury's poles. The floors of craters at the poles receive no direct sunlight at all because the crater walls block the low-angle solar rays. These permanently shadowed regions are among the coldest places in the inner solar system, despite being on the planet closest to the Sun. The possibility of ice on Mercury was first suggested in the early 1990s, based on Earth-based radar observations. Scientists using the 70-meter Goldstone antenna and the Very Large Array radio telescope detected highly reflective regions near Mercury's north and south poles. When radar waves bounced off these regions, they returned signals characteristic of ice. The radar bright spots correlated with the locations of large impact craters, known from Mariner 10 images, craters whose floors could plausibly be in permanent shadow. For 2 decades, the evidence remained circumstantial. Mariner 10 had imaged less than half of Mercury's surface, and its coverage of the polar regions was limited. Scientists could hypothesize that the radar bright spots corresponded to ice in shadowed craters, but they could not prove it directly. Messenger changed everything. When Messenger entered orbit around Mercury in 2011, one of its primary objectives was to investigate the polar deposits. The spacecraft carried a suite of instruments capable of mapping Mercury's surface, measuring its composition, and probing the shadowed polar regions in ways impossible from Earth. Over the following years, Messenger accumulated overwhelming evidence that the radar-bright polar deposits are indeed water ice. Images from Messenger's camera system confirmed that all the radar-bright features at Mercury's North Pole lie within regions of permanent or near-permanent shadow. The spacecraft's laser altimeter fired more than 10 million laser pulses at Mercury's surface, mapping the topography with unprecedented precision. When the laser altimeter measured the reflectance of the polar regions at near-infrared wavelengths, it found that the coldest areas, those in permanent shadow at the highest latitudes, were unusually bright, consistent with exposed water ice on the surface. But the story has an additional layer of complexity. In many of the radar-bright craters, particularly those at slightly lower latitudes where temperatures are somewhat warmer, the surface appeared dark rather than bright at optical and infrared wavelengths. Yet these same areas showed up bright in radar observations. This apparent contradiction puzzled scientists until they developed thermal models of Mercury's polar regions using the actual topography measured by Messenger. The solution involves a thin layer of dark organic material covering the ice. In areas where temperatures are cold enough for ice to be stable on the surface, the ice is exposed and appears bright. But in areas where surface temperatures rise above approximately 100 Kelvin during some part of the Mercurian day, pure ice at the surface would sublimate away. In these regions, ice exists not at the very surface, but buried beneath a layer of dark material, perhaps 10 to 20 centimeters thick. This dark covering insulates the ice below, protecting it from the modest heat that occasionally reaches these areas. What is this dark material? Scientists believe it is likely a mixture of complex organic compounds delivered to Mercury by the same comets and asteroids that brought the water ice. When volatile, rich objects impact Mercury, they deposit water and organic materials across the planet's surface. Most of this material is quickly destroyed by the intense solar radiation and extreme temperatures. But at the poles in permanently shadowed regions, both water and organic molecules can survive indefinitely. Over time, the organics are darkened by radiation, forming the black deposits that cap the ice in warmer shadowed regions. The amount of ice at Mercury's poles is substantial. Scientists estimate that the North Polar deposits alone contain on the order of 100 billion to 1 trillion kilograms of ice, equivalent to a layer roughly 2 to 3 miles thick if spread over an area the size of Washington, D.C. Additional ice exists at the South Pole, though Messenger's orbit provided less detailed coverage of that region. The ice may be relatively young by geological standards, perhaps only tens of millions of years old, suggesting that Mercury's polar ice deposits are continually replenished by comet and asteroid impacts. The process of how water reaches Mercury and becomes trapped at the poles is a story of cosmic delivery and thermal physics. Comets and water-rich asteroids have bombarded the inner solar system throughout its history, occasionally striking Mercury. When such an object impacts Mercury, the water it carries is vaporized and dispersed across the planet. Most of this water is quickly lost to space, decomposed by solar ultraviolet radiation or swept away by the solar wind. But some water molecules, bouncing across the surface in a random walk driven by thermal motions, eventually reach the polar regions. Once a water molecule enters a permanently shadowed crater, it is effectively trapped. The temperatures are so low that the molecule cannot gain enough thermal energy to escape. Over millions and billions of years, these trapped molecules accumulate, building up the ice deposits that we detect today. More recent studies have suggested that the ice inventory on Mercury may be even larger than initially estimated. Beyond the large craters with known ice deposits, researchers have identified many smaller, permanently shadowed regions called microcold traps scattered across Mercury's polar regions. These small shadows, found on poleward-facing slopes and within small craters, could collectively harbor significant additional ice. If these microcold traps are indeed ice-filled, they would substantially increase the total ice inventory on Mercury. One study published in 2017 identified ice deposits in 3 additional large craters at Mercury's North Pole: Chesterton, Tolkien, and Tryggvadatur. Together, these 3 ice sheets cover an area of about 3,400 square kilometers, roughly the size of Rhode Island. But perhaps more importantly, the study also found that the terrain between the large craters is slightly brighter than typical Mercury surface, suggesting the presence of many small ice deposits below the resolution of the instruments. These findings imply that Mercury's polar ice could be distributed across a much larger area than previously recognized. The organic compounds associated with the polar ice deposits add another dimension of interest. When scientists analyzed the pattern of bright and dark materials in Mercury's polar craters, they found that exposed ice correlates with the coldest temperatures, while dark material correlates with areas that are slightly warmer but still cold enough to preserve buried ice. The dark material appears to be a lag deposit, the residue left behind when ice sublimates away from a surface too warm to preserve ice at the very surface. This lag deposit must be rich in organic compounds to have such a low reflectivity. Where did these organics come from? The most likely answer is the same place the water came from: comets and asteroids. These objects contain not just water ice, but also a variety of carbon-bearing compounds, including amino acids and other molecules relevant to prebiotic chemistry. When a comet strikes Mercury, these organics are delivered along with the water. In the cold traps, they accumulate alongside the ice. Over time, exposure to cosmic rays and solar energetic particles polymerizes and darkens the organic material, creating the black deposits that insulate the ice below. The discovery of ice and organic compounds on Mercury has implications beyond geology. Understanding how water and organics were delivered to Mercury and preserved over billions of years helps scientists piece together the story of how volatiles were distributed throughout the early solar system. The same processes that brought water to Mercury likely brought water to Earth and the other inner planets. In a sense, Mercury's polar ice deposits are windows into the history of water in our cosmic neighborhood. Mercury does not have a true atmosphere in the conventional sense. It lacks the substantial gaseous envelope that surrounds Earth, Venus, or even Mars. What Mercury has instead is an exosphere, an incredibly tenuous collection of atoms, so sparse that they are more likely to escape into space or fall back to the surface than to collide with each other. Mercury's exosphere is so thin that its total mass, if compressed to Earth's atmospheric pressure, would occupy a volume smaller than a typical living room. Despite its tenuousness, Mercury's exosphere is surprisingly complex and dynamic. It contains atoms of hydrogen, helium, oxygen, sodium, potassium, calcium, and magnesium, among other species. Each of these components has different sources, different distributions across the planet, and different ultimate fates. Studying Mercury's exosphere provides insights into the interactions between the planet's surface, the solar wind, and the sun's radiation. Sodium is the most prominent component of Mercury's exosphere, at least in terms of how easily it can be detected from Earth. The sodium atoms in Mercury's exosphere were first discovered in 1985 by astronomers Drew Potter and Tom Morgan, who detected the characteristic orange glow of sodium emission lines. Potassium was discovered the following year. Both elements are present in Mercury's surface rocks and are liberated into the exosphere by various processes. The exosphere is generated by a combination of mechanisms. Some atoms are sputtered from the surface when energetic particles from the solar wind strike Mercury and knock atoms loose. Others are released through photon-stimulated desorption, where solar ultraviolet light provides enough energy to kick atoms off the surface. Micrometeoroids constantly bombard Mercury, vaporizing small amounts of surface material upon impact. Mercury's high daytime temperatures cause some atoms to evaporate thermally from the surface rocks. Each of these processes contributes to the exosphere differently for different elements, resulting in the complex spatial and temporal patterns that scientists have observed. One of the most visually striking features associated with Mercury's exosphere is its sodium tail. The sodium atoms released into the exosphere are subject to radiation pressure from sunlight. Sodium atoms strongly absorb and re-emit light at particular yellow-orange wavelengths. When they absorb solar photons, they receive a tiny push in the direction the light was traveling, away from the sun. This radiation pressure accelerates sodium atoms away from Mercury and into interplanetary space, forming a long tail of sodium gas stretching behind the planet in the anti-sun direction. Mercury's sodium tail has been observed extending for enormous distances, up to millions of kilometers, or roughly 1/400 Mercury radii behind the planet. The tail appears to be highly variable, changing in intensity and shape over time, as conditions on Mercury's surface and in the solar wind fluctuate. Ground-based telescopes and the Messenger spacecraft have studied the tail in detail, revealing the complex interplay between the Sun and Mercury's surface environment. Calcium is another interesting exospheric component. Unlike sodium, calcium atoms appear to be distributed differently, concentrated in a hot corona around Mercury, with temperatures reaching 12,000 to 20,000 Kelvin. The calcium corona was somewhat unexpected and suggests that the processes generating calcium atoms differ from those producing sodium. Magnesium, discovered by Messenger during its flybys, shows yet another distribution pattern, with different concentrations above Mercury's north and south poles that vary over time. MESSENGER also detected a variety of unexpected ions in Mercury's environment. The spacecraft's fast imaging plasma spectrometer found ionized water vapor, hydroxyl ions, and even hydronium ions, the positively charged molecules that form when water molecules pick up an extra proton. These detections were surprising because water is generally not expected to survive long on Mercury's surface. The presence of water-related ions suggests active processes liberating water from Mercury's surface, possibly from the polar ice deposits or from water generated by solar wind protons interacting with oxygen-bearing minerals in the rocks. Mercury's weak magnetosphere interacts with the exosphere in complex ways. The magnetic field funnels charged particles toward the polar regions, where they can sputter atoms from the surface more efficiently than at the equator. MESSENGER observed that sodium emissions are sometimes concentrated near Mercury's magnetic poles, suggesting a direct connection between magnetospheric dynamics and exosphere generation. The magnetic field also affects how exospheric ions are transported, picked up by the solar wind, and lost to space. The solar wind bombards Mercury directly because the planet's magnetic field is too weak to provide complete shielding. MESSENGER scientists described Mercury's magnetosphere as leaky, allowing solar wind particles to penetrate much closer to the surface than they can at Earth. The magnetic tornadoes discovered during MESSENGER's flybys are one mechanism by which the solar wind gains access to Mercury's surface. These twisted magnetic structures connect the interplanetary magnetic field directly to Mercury's magnetic field, creating channels through which charged particles can flow. Mercury's interaction with the solar wind represents one of the most dynamic magnetospheric environments in the solar system. The relative sizes of Mercury and its magnetosphere are such that the entire system responds rapidly to changes in solar wind conditions. Features that take hours to develop in Earth's magnetosphere can form in minutes at Mercury. Studying Mercury's magnetosphere helps scientists understand the fundamental physics of how magnetic fields interact with plasmas, with implications for understanding space weather throughout the solar system. Mercury has played a crucial role in the history of physics, serving as an unlikely testing ground for one of the greatest theories ever developed, Albert Einstein's general theory of relativity. The story begins in the 19th century with careful observations of Mercury's orbit and leads to a fundamental shift in our understanding of gravity itself. As astronomers tracked Mercury's motion across the sky with increasing precision, they noticed a puzzling discrepancy. Mercury's orbit is an ellipse, like all planetary orbits, with the Sun at one focus. The point where Mercury comes closest to the Sun, called perihelion, should remain fixed in space if Mercury and the Sun were the only two objects in the universe. However, the gravitational influence of the other planets causes Mercury's orbit to precess, meaning the orientation of the ellipse slowly rotates over time. The perihelion point shifts, tracing out a rosette pattern over millions of years. Astronomers calculated the expected precession of Mercury's perihelion due to the gravitational tugs of Venus, Earth, Mars, Jupiter, and the other planets. They also accounted for the slight oblateness of the Sun. When they added up all these effects using Newtonian mechanics, they predicted that Mercury's perihelion should precess by about 532 arcseconds per century. but observations showed that Mercury's perihelion actually precesses by about 574 arcseconds per century. There was a discrepancy of approximately 43 arcseconds per century that could not be explained by Newtonian physics. This anomalous precession was recognized by French astronomer Urbain Le Verrier in 1859. Le Verrier was famous for having predicted the existence and location of Neptune based on irregularities in the orbit of Uranus, a triumph of Newtonian mechanics. Naturally, he suspected that another undiscovered planet might be responsible for the anomaly in Mercury's orbit. Le Verrier proposed that a small planet, even closer to the Sun than Mercury, might exist and perturb Mercury's orbit. This hypothetical planet was given the name Vulcan. For decades, astronomers searched for Vulcan. Several claimed to have observed it during solar eclipses or as a dark spot crossing the face of the Sun during transits. But none of these sightings could be confirmed, and the searches grew increasingly comprehensive and sophisticated. By the early 20th century, photographic surveys of the region around the Sun during total solar eclipses had effectively ruled out any planet large enough to account for Mercury's orbital anomaly. Vulcan did not exist. The resolution came from an entirely different direction. In 1915, Albert Einstein published his general theory of relativity, a revolutionary new theory of gravity that replaced Newton's concept of gravitational force with the idea that mass curves the fabric of space-time. Objects moving through curved space-time follow paths called geodesics, which appear to us as the curved trajectories of falling objects and orbiting planets. Einstein realized that his theory made a specific prediction about Mercury's orbit. In the curved space-time near the Sun, Mercury's orbit would precess slightly more than predicted by Newtonian mechanics. Einstein calculated this extra precession and found it to be 43 arcseconds per century, exactly matching the observed anomaly. The puzzle that had vexed astronomers for over half a century was solved in a single stroke. This was one of the three classical tests of general relativity that Einstein proposed, along with the bending of starlight by the Sun's gravity and the gravitational redshift of light. The perihelion precession of Mercury was the only one of these three tests that could be checked immediately against existing data, and its success gave Einstein immense confidence in his theory. He wrote to a friend that he had been beside himself with joy for days after completing the calculation. The precession of Mercury's perihelion remains one of the most elegant confirmations of general relativity. Mercury is unique among the planets in the magnitude of this effect because it is closest to the Sun, where space-time curvature is strongest, and because its highly eccentric orbit makes the precession easier to measure. The other planets also experience relativistic perihelion precession, but the effect is smaller and was not measurable until much later. Today, measurements of Mercury's orbital motion are extraordinarily precise. Radio tracking of spacecraft orbiting and flying by Mercury, combined with radar observations from Earth, allows scientists to measure Mercury's position and velocity with remarkable accuracy. These measurements confirm that general relativity correctly describes Mercury's motion to high precision. Any deviations would indicate new physics beyond Einstein's theory, so Mercury continues to serve as a valuable laboratory for testing fundamental physics. The story of Mercury's perihelion precession is a reminder of how the smallest details, in this case a discrepancy of 43 arcseconds per century in the orbit of a tiny planet, can have profound implications. What seemed like a minor anomaly in celestial mechanics turned out to herald a revolution in our understanding of gravity, space, and time. Mercury, the swift messenger of the gods, carried a message from the universe about the deep structure of reality itself. The term arcsecond deserves some explanation for those unfamiliar with astronomical measurements. A full circle contains 360 degrees. Each degree is divided into 60 arc minutes, and each arc minute is divided into 60 arc seconds. An arc second is therefore 1/3600th of a degree, an incredibly small angle. For comparison, the full moon appears about half a degree across, or about 1/800 arc seconds. The anomalous precession of Mercury's perihelion, at 43 arc seconds per century, represents a shift of only about 0.0012 degrees every 100 years. That astronomers could measure such a tiny effect before the era of electronic instruments is a testament to the precision and dedication of 19th century observational astronomy. The resolution of Mercury's anomalous precession was one of the first great triumphs of general relativity, coming at a time when Einstein was still developing his theory and desperately seeking observational confirmation. When his calculations predicted the exact value that observers had measured, it gave him profound confidence that he was on the right track. The perihelion precession remains one of the standard tests of general relativity, and modern measurements using radar and spacecraft tracking confirm Einstein's prediction to extraordinary precision. Mercury's importance to physics extends beyond general relativity. The planet's proximity to the Sun makes it an ideal target for studying the solar gravitational field and for testing alternative theories of gravity. Any theory that hopes to replace or extend general relativity must correctly predict Mercury's orbital motion. So far, no credible alternative has been found that matches general relativity's success in explaining Mercury's behavior. The exploration of Mercury by spacecraft has been a challenging endeavor from the very beginning. Mercury is, paradoxically, one of the most difficult planets to reach in the entire solar system. While it is relatively close to Earth in absolute distance, the dynamics of orbital mechanics make getting to Mercury an arduous journey that requires careful planning and significant time. The difficulty lies in Mercury's position deep within the Sun's gravitational well. A spacecraft leaving Earth and falling toward the Sun gains enormous speed as it approaches the inner solar system. To enter orbit around Mercury, a spacecraft must somehow shed this excess velocity, or it will simply fly past the planet at high speed. Using conventional rocket propulsion to slow down would require prohibitive amounts of fuel. The solution is to use gravity assists, flying past planets in precisely calculated trajectories that allow their gravity to alter the spacecraft's speed and direction. Mariner 10 was the first spacecraft to visit Mercury, conducting 3 flybys between 1974 and 1975. Launched on November 3, 1973, Mariner 10 used a gravity assist from Venus to redirect its trajectory toward Mercury, becoming the first spacecraft to use a gravity assist to visit another planet. This technique was suggested by Italian mathematician and engineer Giuseppe Colombo, after whom the Bepi Colombo mission would later be named. Mariner 10 flew past Mercury 3 times, on March 29, 1974, September 21, 1974, and March 16, 1975. Due to the geometry of its orbit and the 3-2 resonance of Mercury's rotation, Mariner 10 saw essentially the same hemisphere of Mercury during each flyby. The spacecraft imaged about 45% of Mercury's surface, revealing a heavily cratered moon-like landscape. Mariner 10 also discovered Mercury's magnetic field, one of the mission's most surprising findings. The spacecraft measured surface temperatures and studied Mercury's thin exosphere before exhausting its attitude control gas and ending its mission. For more than 3 decades after Mariner 10, no spacecraft visited Mercury. The challenges of reaching the planet, combined with limited scientific interest, compared to more glamorous targets like Mars and the outer planets, kept Mercury on the sidelines of planetary exploration. This changed with Messenger. Messenger, which stands for Mercury Surface, Space Environment, Geochemistry, and Ranging, was launched on August 3, 2004. Its journey to Mercury was one of the most complex ever undertaken, requiring 1 flyby of Earth, 2 flybys of Venus, and 3 flybys of Mercury, over 6.5 years before the spacecraft finally entered orbit on March 18, 2011. Each gravity assist fine-tuned Messenger's trajectory and reduced its velocity relative to Mercury, allowing it to be captured into orbit with the fuel it carried. Messenger's orbital mission revolutionized our understanding of Mercury. The spacecraft's highly elliptical orbit brought it as close as 200 kilometers to Mercury's surface at its lowest point, while swinging out to nearly 15,000 kilometers at its highest. This orbit allowed Messenger to survive the intense heat from Mercury's surface, while still making detailed observations during close approaches. Over 4 years of orbital operations, Messenger transformed Mercury from a mysterious world known only from glimpses into one of the best characterized planets in the solar system. The spacecraft captured more than 291,000 images, mapping the entire surface at resolutions far exceeding anything previously available. It measured Mercury's composition using X-ray, gamma-ray, and neutron spectrometers, discovering the high sulfur content and low iron content of the surface that constrains theories of the planet's formation. Messenger mapped Mercury's gravity field and topography, revealing details of the interior structure. It characterized the magnetic field's peculiar offset and observed the dynamic magnetosphere. And as we have discussed, Messenger confirmed the presence of water ice at the poles and discovered features like hollows that indicate ongoing geological activity. The Messenger mission ended on April 30, 2015, when the spacecraft exhausted its propellant and crashed into Mercury's surface at a speed of about 14,080 kilometers per hour. The impact created a new crater on Mercury, estimated to be about 16 meters in diameter, near the Janacek crater in a region called Suisse Planitia. Messenger's legacy lives on in the data it returned, which scientists continue to analyze to this day. The next chapter in Mercury exploration is being written by Bepi Colombo, a joint mission of the European Space Agency and the Japan Aerospace Exploration Agency. Named after Giuseppe Colombo, the scientist who first proposed using gravity assists to reach Mercury, Bepi Colombo launched on October 20, 2018, and is currently on its 8-year journey to the innermost planet. Bepi Colombo is actually 2 spacecraft traveling together: the Mercury Planetary Orbiter built by ESA and the Mercury Magnetospheric Orbiter called MEO, built by JAXA. The 2 orbiters are currently attached to a transfer module that provides propulsion and power during the cruise to Mercury. When Bepi Colombo arrives at Mercury, currently expected in November 2026, after a delay due to a thruster issue, the transfer module will be jettisoned and the two orbiters will separate into different orbits around Mercury. The dual spacecraft design allows Bepi Colombo to study Mercury from two different perspectives simultaneously. The Mercury Planetary Orbiter will focus on the planet itself, mapping the surface composition, studying the interior structure, and observing the exosphere. The Mercury Magnetospheric Orbiter will concentrate on Mercury's magnetic field and its interaction with the solar wind. Together, the two spacecraft will provide a comprehensive view of Mercury and its environment that exceeds the capabilities of any single mission. The Mercury Planetary Orbiter carries 11 scientific instruments. Bella, the Bepi Colombo laser altimeter, will map Mercury's topography with unprecedented precision, revealing the shapes of craters, mountains, and other surface features. Murtis, the Mercury radiometer and thermal infrared spectrometer, will determine the mineralogical composition of the surface by measuring how rocks emit thermal radiation. This instrument has already demonstrated its capabilities during the recent flybys. Symbio-SWI-S is an integrated package of 3 cameras that will image Mercury's surface in multiple wavelengths, create stereo views for topographic mapping, and search for subtle color variations that indicate different rock types. Other instruments on the Mercury Planetary Orbiter include MIX-S, the Mercury Imaging X-ray Spectrometer, which will measure X-rays fluorescently emitted from the surface when bombarded by solar X-rays, revealing elemental abundances. Phoebus, the Probing of Hermian Exosphere, by ultraviolet spectroscopy instrument, will study Mercury's exosphere by analyzing ultraviolet light. Serena is a suite of instruments to study the neutral and charged particles in Mercury's environment. The magnetometer will map Mercury's magnetic field, while the accelerometer will measure subtle variations in Mercury's gravitational field that reveal information about the interior structure. The Mercury Magnetospheric Orbiter, built by JAXA, carries 5 instruments focused on the space environment around Mercury. The Mercury Plasma Particle Experiment Suite includes multiple sensors to measure electrons, ions, and energetic particles in the magnetosphere. The Plasma Wave Instrument will detect electric and magnetic fluctuations associated with plasma waves. The magnetometer on this orbiter will complement the one on the European orbiter, allowing scientists to distinguish between spatial and temporal variations in the magnetic field. The two orbiters will operate in different orbits, optimized for their scientific objectives. The Mercury Planetary Orbiter will follow a relatively close polar orbit, passing as near as 480 kilometers to the surface at its lowest point. This close approach is essential for high-resolution imaging and compositional measurements. The Mercury Magnetospheric Orbiter will have a more distant, highly elliptical polar orbit, ranging from about 590 kilometers at its closest to over 11,000 kilometers at its farthest. This elongated orbit allows it to sample different regions of Mercury's magnetosphere as it swings from near the planet to well outside the bow shock. Bepi Colombo's journey to Mercury has already yielded scientific discoveries. The spacecraft has performed 9 gravity assist flybys, including 1 of Earth, 2 of Venus, and 6 of Mercury. During the Mercury flybys, which brought Bepi Colombo as close as 165 kilometers to the surface, the spacecraft's instruments collected data even though they were not in their final orbital configuration. These flyby observations have revealed new details about Mercury's magnetosphere, including the detection of particles with energies never before observed at Mercury, evidence for a ring current of trapped hydrogen ions, and cold plasma ions of oxygen, sodium, and potassium, likely ejected from the surface by micrometeoroids or the solar wind. During the fifth Mercury flyby in December 2024, Bepi Colombo made history by observing Mercury for the first time in mid-infrared light using the MIRDIS instrument. These observations revealed variations in temperature and composition across Mercury's cratered surface, providing a tantalizing preview of the detailed mineralogical mapping that will be possible once Bepi Colombo enters orbit. During the sixth and final Mercury flyby in January 2025, Bepi Colombo imaged permanently shadowed craters near Mercury's North Pole, including Prokofiev, Kandinsky, Tolkien, and Gordimer, where water ice may lurk in the eternal darkness. When Bepi Colombo begins its primary science mission in 2027, it will address many of the questions that Messenger left unanswered. Scientists hope to learn more about Mercury's composition and how it varies across the surface, which will constrain theories of the planet's formation. They want to understand the offset magnetic field and the dynamics of Mercury's magnetosphere in greater detail. They will investigate the polar ice deposits to determine their extent, composition, and age, and they will search for new surprises that Mercury undoubtedly still holds. The exploration of Mercury exemplifies the spirit of human curiosity. Here is a world that is difficult to reach, challenging to observe, and hostile to any conceivable form of life. Yet we send spacecraft to study it, not because it offers resources we might exploit or a destination we might someday visit in person, but because we want to understand our solar system and our place within it. Mercury is a piece of the puzzle, a record of conditions and processes from the earliest days of planetary formation. By studying Mercury, we learn about our cosmic origins. Looking to the future, scientists have proposed various concepts for further Mercury exploration beyond Bepi Colombo. One intriguing possibility would be a Mercury lander, a spacecraft that would touch down on the surface and conduct in situ measurements of the rocks and soil. Such a mission would face enormous technical challenges. A lander on Mercury's day side would need to survive temperatures exceeding 400 degrees Celsius, requiring advanced thermal protection systems. A lander in the polar regions could potentially take advantage of the more moderate temperatures in permanently shadowed areas, but reaching these locations precisely would be extremely difficult. Another possibility is a Mercury orbiter carrying instruments capable of detecting seismic waves generated by natural events, like meteorite impacts or possible internal quakes. By measuring how these waves travel through Mercury's interior, scientists could directly probe the structure of the core and mantle in ways that surface observations cannot. Understanding Mercury's interior structure would constrain models of its formation and evolution and help explain the planet's unusual composition. Some visionary scientists have even proposed missions that would attempt to sample Mercury's polar ice deposits and return that material to Earth for laboratory analysis. Such a sample return mission would be extraordinarily challenging and expensive, but the scientific payoff could be immense. Analyzing Mercury's polar ice would reveal its composition, its age, and its origin, providing direct evidence about how water and other volatiles were delivered to the inner solar system. The organic compounds mixed with the ice could be studied in detail, potentially revealing information about the building blocks of life that were present in the early solar system. Mercury's extreme environment makes it a natural laboratory for understanding processes that operate under conditions found nowhere else in our solar system. The planet experiences the most intense solar radiation of any planet, the fastest orbital and rotational dynamics, the widest temperature swings, and among the most active space weathering environments. Studying how Mercury responds to these extreme conditions helps scientists understand the fundamental physics of planetary surfaces, atmospheres, magnetospheres, and interiors. Mercury also serves as a point of comparison for understanding exoplanets orbiting close to other stars. Astronomers have discovered thousands of exoplanets, and many of them orbit their host stars at distances comparable to or even smaller than Mercury's orbit around the Sun. These close-in exoplanets experience similar extremes of temperature, radiation, and stellar wind bombardment. Understanding how Mercury has evolved and what it looks like today provides a template for interpreting observations of these distant worlds. In a sense, Mercury is our local example of a class of planet that may be common throughout the galaxy. As you absorb everything we have explored tonight, consider the remarkable journey that Mercury represents, both for the planet itself and for our understanding of it. Here is a world forged in the fires of the early solar system, possibly sculpted by catastrophic collisions, shrinking slowly over billions of years as its iron heart cools. It is a world of extremes where the line between scorching heat and freezing cold can be as narrow as the shadow of a crater rim. It harbors ice at the gates of hell, organic compounds in the most radiation-drenched environment in the inner solar system, and a magnetic field that should not exist according to some models, yet stubbornly persists. Mercury challenged our understanding of gravity itself, revealing, through its subtle orbital dance, a flaw in Newtonian mechanics that only Einstein's revolutionary theory could explain. It has been visited by only 3 spacecraft in all of human history, yet those missions have transformed it from a distant point of light into a world we can map, measure, and begin to comprehend. And there is still so much more to learn. The questions that remain about Mercury are profound. How exactly did the planet form with such an enormous iron core? What processes delivered water and organic compounds to a world so close to the Sun? And how have they survived for billions of years? What drives the offset of Mercury's magnetic field? And what does it tell us about the dynamics deep within the planet's core? Are hollows still actively forming today? And if so, what does that tell us about ongoing processes on Mercury's surface? How has Mercury's surface been modified by space weathering over billions of years? And what can we learn about the early solar system from its ancient geological record? Bepi Colombo will address many of these questions when it begins its full science operations in 2027, following its arrival in Mercury orbit in late 2026. But undoubtedly, the answers it provides will raise new questions that we cannot yet imagine. That is the nature of scientific exploration. Each discovery opens new doors, each answer raises new questions, and each mission lays the groundwork for the next. Mercury will continue to challenge and fascinate us for generations to come. The next time you find yourself awake before dawn or lingering after sunset, look toward the horizon where the sun has just risen or is about to set. If the timing is right, you may glimpse a small, bright point of light close to the glow of twilight. That is Mercury, the swift messenger, racing around the sun faster than any other planet, carrying secrets about the formation of worlds and the nature of space and time itself. Ancient astronomers watched that same point of light and wondered what it was. We are privileged to live in an age when we can actually find out. Mercury's elusiveness in our sky has made it something of a challenge for amateur astronomers throughout history. Unlike Venus, which can appear brilliant and obvious, or Mars, which can glow red and conspicuous during oppositions, Mercury requires dedication and planning to observe. You need to know when Mercury is at favorable elongation. You need a clear horizon, and you need to be watching at precisely the right time. Yet for those who make the effort, seeing Mercury is deeply satisfying. There is something special about catching sight of this tiny world that darts so close to the sun that the ancients thought it was two different objects. Binoculars can help you spot Mercury when conditions are right, and small telescopes can reveal the planet's phases. At greatest elongation, when Mercury appears farthest from the sun, you can see it displaying a half-illuminated face, similar to a first or last quarter moon. As Mercury moves closer to the sun in our sky, it shows a crescent phase, and as it moves to the far side of the sun, it becomes gibbous or nearly full, though at that point, it is usually lost in the solar glare. Observing Mercury's phases is a tangible connection to the astronomical observations that helped establish our understanding of the solar system. Thank you for joining me on this journey to the extreme world closest to the sun. If you found this exploration meaningful, or if it helped you relax and drift into a state of calm curiosity, please consider liking and subscribing to the channel. Your support helps me continue making these deep explorations of our universe and the wonders it contains. Until next time, keep looking up at the night sky. Keep wondering about the distant worlds that share our solar system. And remember that even the smallest, most seemingly inhospitable planet has stories to tell if we have the patience and ingenuity to listen. Sleep well tonight, knowing that somewhere in the inner solar system, Mercury is racing around the sun, its ancient surface baking under relentless radiation, while ice slumbers in its polar shadows. It is a world of contradictions, a messenger from the dawn of the solar system, and a reminder that the universe is far stranger and more wonderful than we could ever imagine on our own. As you drift towards sleep, perhaps imagine yourself standing on Mercury's terminator, the boundary between day and night. Behind you, the sun blazes in a darkened sky, its enormous disk casting long shadows across the cratered terrain. Before you, darkness stretches to the horizon, punctuated by the faint glow of starlight reflecting off ancient rocks. The temperature is changing rapidly as you stand there, the ground beneath your feet cooling from hundreds of degrees to hundreds below zero. The silence is absolute, for there is no air to carry sound. Above, the stars shine steadily, unblinking in the airless void. And somewhere in that star-studded sky, a blue dot hangs, the planet where humans dream of distant worlds and send their robotic emissaries to explore the cosmos. Good night.